positive and the chlorine is having a delta negative charge. Got it? So this delta positive charge will attract someone which has electron pair, unshared pair of electron, and that is known as nucleophile. The carbon actually, so this is the nucleophile. Here I've shown you the exact mechanism. And because on one side you have a Cl or Br, you can see over here, and this forces the nucleophile to come from the side opposite. So this side you have a Br or Cl. The nucleophile is actually coming from the side opposite to the leaving group. Okay, so nucleophile approaches from the back side because on one side you have bromine, so the nucleophile can't come from that side. Okay, clear? So I hope that is clear to you, right? And now you can see that once this nucleophile started joining itself, it has started giving its electron pair. So this bonds start forming, but carbon can make only 4 bonds. So if the nucleophile electron density is being given to the carbon, the Br should take away the electron density. Okay, so this bond start breaking. What happened to the other 3 bonds? They become flat. So this is the transition state. The transition state of the substitution reaction in which the Br is being replaced by a nucleophile. Got it? So once the reaction gets completed, this nucleophile completely attaches itself and the Br minus completely comes out. That's what we know. And this is nucleophilic substitution reaction. This has happened in just one step. I am showing you step by step. But this is just a single step in which the nucleophile hits the carbon and just it pushes out the halide ion. Okay, so this is Sn2. And because in this reaction we are having 2 molecules participating, right? So 2 molecules participating. So this is bimolecular reaction. The one is the nucleophile, another one is the substrate. Got it? Understood? And if there is a chiral carbon, yesterday we have seen chiral carbon, there is an inversion inversion of the bonds which happens at the chiral carbon, because as I've shown you, from one side the nucleophile approaches, the other 3 bonds will get flipped to the other side. So there is an inversion happening, right? So this is how the reaction proceeds. And what happens to the energy? This is the energy profile during the progress of the reaction. When there is a transition state, the energy has reached its maximum level. Okay, this inversion is known as Walden inversion, and this reaction is known as substitution nucleophilic bimolecular because it is caused by nucleophile, and there are 2 molecules involved in it. Substitution because one group is replaced by another group. Nucleophilic because it is caused by nucleophile, and bimolecular that you must have studied in your 12th. Walden inversion has happened, so look carefully. A lot of questions are being asked on it. How they can be asked? So you can see over here, if you have Br on this side, the I minus, if you react, this is Finkelstein reaction we have seen yesterday. So I minus is going to come and join itself from the opposite side. So look, these 3 bonds which have not participated, they flipped on the other side like this. So join I on the side exactly opposite to that of Br. The other 3 bonds, just shift them like this. Okay, so there is a flipping of carbon atom, inversion of configuration. This is known as Walden inversion. What happens to this? This OH minus, okay, this OH minus actually attacks from the lower side because this Br is Br is actually pointing upwards, so the OH minus should attack from the lower side. So look, this OH minus is now below the plane. This is the nucleophile. This Br is coming towards us. It is above the plane, and this is the nucleophile SET. So this should attack from the back. So SET will get attached from the back side. This Br is above the plane, and if you put acetate ion, which is the nucleophile carrying a lone pair, that should get attached from the back side. Okay, so this is how you need to do the Walden inversion on Sn2 reaction. I hope this is clear to everyone. Got it? This is how Walden inversion, it can be asked in different ways. There are questions related to it, you can see. Okay, a lot of questions. So so this is substitution nucleophilic bimolecular. What are the factors? Let's get into the detail. So because two molecules are colliding simultaneously, the rate is directly proportional to the concentration of each one of them, the alkyl halide as well as the nucleophile. Okay, so this is a second order reaction. The rate of Sn2 is directly proportional to the concentration of, because they are colliding, they are reacting with each other, so you need the concentration. If you increase the concentration of each one of them, the more collisions are going to happen and the rate is going to increase. So here you can see, if you double the concentration of the substrate CS3Cl or CS3Br, whatever the substrate which you have taken, the rate will get double. If you double the concentration of the nucleophile, then also the rate will get double. If you double the both the concentration, the rate will become 4 times. Got it? And how the alkyl group affects the rate of Sn2? Alkyl group, if it is large enough, if it is larger alkyl group, then those alkyl groups are going to hamper the approach of nucleophile, as we have seen here. Look, if these alkyl groups are bigger and bigger, what is going to happen? The nucleophile will feel more repulsive force. Okay, and it will be difficult for the nucleophile to come in and get attached to the carbon. So rate is, or the speed of the Sn2 is going to come down. So here you can see, with branching, as the branching increases, rate of Sn2 decreases. I hope this is clear to everyone. So let's do this question very quickly. For an Sn2 reaction, which of the following statements are true? This is one or more than one correct option. So which of the following statement is or are true? So first statement says the rate of reaction is independent for Sn2s. Bimolecular substitution rate is independent of the concentration of nucleophile. No, this is incorrect. Just now we have seen rate was dependent on the concentration of the nucleophile. That's what we are seeing, because both the nucleophile and the substrate were actually attacking, they were interacting with each other. So rate actually is directly proportional to the concentration of each one of them. The nucleophile attacks the carbon on the side of the molecule opposite to the group being displaced. Yes. And this leads to inversion of the configuration. This is true. The reaction proceeds with the simultaneously bond formation and rupture. This is also true. Bond formation with whom? Bond formation with the nucleophile. And bond breaking with the leaving group. Okay, so the right answer is option B and C. So I hope this is clear. You can stop me anytime if something is not clear. Okay, so now let's move to the next question. Which of the following statement is or are true? Yeah. So we need to calculate which of the following statement is or are true. Okay, just we need to look at the structure. So first one is Cl. It will react more readily than Br. No, the Br is a bigger atom. Its bond is larger, its bond is weaker, and it can break more easily than Cl. And if you have fluorine, then it is slower than chlorine, Cl. So this is incorrect because the rate should be in this way. Fluoride, Rf, then RCl, then RBr, and then you have Ri. So this is incorrect because it is saying chloride is more reactive than bromide. No. You have I, it reacts more rapidly than this is also I, but this is more branched, so rate of reaction will be slower, and this will be higher for this one. So this is true. Next statement, you have Br will react more rapidly than this one, though both are primary, but in this case there is more branching close to the primary carbon where the attack of the nucleophile is happening, and this is less branched, so it is going to be more reactive than this one. Okay, so this is also correct. Next is this one will react more rapidly than this. Okay, this is CH2Br, this is CH2Br, this is benzene, this is NO2, this is OCH3 at. Okay, so let's see how we need to discuss this. CH2Br is there. Okay, this is NO2, right? And this is OCH3. Got it? NO2 actually is electron withdrawing group. So it is going to bring in the positive charge. And because it is positive charge, the positive charge is going to increase on the carbon, and this makes it more susceptible towards the nucleophilic attack. And the Br will come out more easily. But this OCH3 is electron donating group, and it increases the electron density on the carbon at the para position. Nucleophile is also carrying its own electron, so nucleophile will feel more repulsion, so attack is going to be difficult. So this is not correct because this will react more rapidly. Okay, so the right options are B and C. I hope this is clear to everyone. Stop me anytime if there is any doubt. Okay, just ask me anytime, any number of times. Okay, so option B and C. So rate is, let me conclude, if you increase the branching, the rate is going to get slowed down. The branching, if it is adjacent to the site of attack, then also the rate will come down. If you put fluorine, the rate is going to come down. Okay, rate increases from F to I. Okay, if you put an electron donating group which increases the electron density, nucleophile also itself is carrying its own electron, so it will stop the income nucleophile, so rate will get slowed down. But if you put an electron pulling group, electron withdrawing group, which is exerting minus R effect, the rate is going to go up. Okay, so these are some of the factors which affect the rate of Sn2. So let's discuss some of this Sn2 reaction. There are questions on the theory. Okay, theory part, on the mechanism part, where the rate is going to be more, where the rate is going to be less. Okay, that is one thing. The other part where the Sn2 comes into picture is the lot of conversions. The lot of conversions happen by Sn2 mechanism, where you displace the iodide or bromide or chloride with the desired functional group which you want to prepare. Okay, so this next slide is about the reactions. Okay, as you can see, this alkyl halides are very reactive and they can be easily substituted, okay, by different groups, right? And these are the nucleophiles. Cn, okay, this one. These are the nucleophiles. So you can prepare ether, and this reaction is none other than Williamson ether synthesis. In which you take an alkoxide ion and an alkyl halide. All of these are conversions which involve substitution reaction. Very simple. If you take this alkyne, terminal alkyne, the H can be removed being acidic and it can come in as a nucleophile, pushing away the Br. This is the table given in NCERT, which helps us to know what is the nucleophile and what is the final product. As you can see over here, this is the nucleophile. This halogen is Cl or Br or I. The nucleophile comes in, pushes out the halogen. And what this nucleophile could be? It could be OH minus. If it is OH minus, you get ROH. Okay. If it is water, then also you get ROH. But the reaction is going to be very slow because water is neutral. If you take an alkoxide ion, the nucleophile is this one, R-O minus, and you get an ether. This is known as Williamson ether synthesis. This is the functional group. If you take I minus as the nucleophile, the I minus is going to come in and it is going to push away the chlorine and bromine. You are going to get Ri, and this was the Finkelstein reaction which we have discussed yesterday. If you want to put F, you require Schwarz reaction where you use AgF. If you want to prepare a amine, you need to take ammonia or NH3 as the nucleophile. The NH3 as a lone pair, it comes into come and join itself to the alkyl group and displacing I. Okay, so you get RNH2. If you get primary, secondary, okay. So this is how you can convert it to various other functional groups. This is very important, and this is the place where most people forget. And this cyanide is actually an ambidentate nucleophile. You can see over here, Cn minus. So it has lone pair on two sides. Normally, the carbon is going to be the attacking side of the nucleophile. You get nitriles or the cyanide because carbon is carrying a negative charge. But if you use silver cyanide, silver actually has a tendency to form covalent bond. So now the carbon is not free to go and attack as a nucleophile. Now the nitrogen end will be the attacking end on the Rx. So you get isocyanide or isonitriles. Same thing you need to remember for KNO2. KNO2 is like this. O minus is the attacking species, atom attacking side of the nucleophile. Because O minus was electron rich, and that is going to attack, and you will get alkyl nitride. But if you use AgNO2, again the same thing has happened. Silver will form a partial bond with ONO. So nitrogen, now oxygen is not free. Nitrogen will be the attracting atom, so you get nitroalkane. If you take RCO minus, then also you get an ester. LH, you get H minus, is the nucleophile you get. This is the reduction reaction. if you use metal salts, so this metal salts of alkyl groups, organometallic compound, this there the metal is connected to carbon, carbon is having a negative charge, and that attacks the Rx. So you get this R dash being attached to Rx. Okay, alkene you are going to get. So this is how you are going to get different compound using this substitution reaction. Okay, and this is the preparation of various functional group. This is the table from NCERT I have taken. Very basic table, but very important. Next reaction is Sn1. This is also telling us how the substitution is going to happen. Right, how the substitution can happen. This is Sn1 reaction. Substitution nucleophilic unimolecular. How it happens? Okay, this is nucleophilic substitution, but in this case, as you can see over here, it is given by bulkier substrate tertiary. Just now we have seen that wherever you had tertiary, there the reaction was very quite difficult. Okay, we have seen here the rate was very slow because the branching hampers the nucleophile to come in and join with the carbon atom. So what does that mean? That the tertiary substrate or the tertiary alkyl halide will not undergo substitution reaction? No. In fact, the tertiary alkyl halide undergo substitution reaction much faster than the primary also. But how it has happened? It has happened not by simultaneous attack and departure of the leaving group. In fact, it has happened by some different mechanism, which is also a nucleophilic substitution reaction. That is Sn1 mechanism. Substitution nucleophilic unimolecular means in the crucial step, only one molecule is involved. There, the two molecules were colliding with one another, so it was bimolecular. So, what is happening? So, first of all, you are taking a tertiary alkyl halide. Next thing which is happening is you have taken a water. Water is a very good polar protic solvent. Okay, it can very easily undergo do hydrogen bonding. Okay, that we know it is a polar solvent. So Br is having a delta minus and carbon is having a delta plus, and you have taken water. So water actually is trying to pull, it will start interacting with the bromide ion through this ion dipole interaction, dipole interaction, and it will try to slowly pull this bromide ion apart. Okay, now so this is the most difficult step, most crucial step, and it is going to be very slow because bond breaking require energy. That is true, and so it is going to require energy. And here you can see the simultaneously you can see how the energy is being changing. You can see the graph rising up abruptly. Okay, because you know that bond breaking require energy, so energy is increasing, and so this is going to be a slowest step of the overall reaction, rate determining step. That's why so whole rate is going to depend on this. You get a cation. Okay, the cation, once you have the cation, now so the crucial step involves only one molecule. That's why it is unimolecular. This is only one molecule is involved. Now the nucleophile comes in and joins itself to the carbocation, because carbocation is actually an electron deficient species, so H2 gets forms a bond with the lone pair. So CO bond is formed and ultimately this H plus is removed and you get a final alcohol. Okay, this is how the energy profile and the energy of the product comes down, as you can see. So this is substitution nucleophilic unimolecular Sn1. This happens at on those substrate which are very bulky, which can form a stable carbocation. So if they are very bulky, nucleophile can't come in and attack. The leaving group can come out easily because the substrates are such that they can form a stable carbocation. Tertiary carbocation are very stable. Okay, and also there is a role of solvent. The solvent which you take, in this case, are polar protect solvent. Protect means the H is directly linked to oxygen or any other electronegative atom. This solvent, polar protect, by saying polar protect, we mean to say that it can form hydrogen bond with the Br minus, or it can form ion dipole interaction with the Br minus. It can help the to pull the Br minus out. Okay, so polar protect solvent is a must for Sn1 reaction. You need a tertiary carbocation or a molecule which can form a carbocation easily. You need a good leaving group which can slowly breaks apart from the substrate, and you need a solvent which is polar protect. Okay, if all these things come together, you see that the mechanism changes to Sn1, which proceeds via carbocation. So there are so many steps, but they are very quickly happening except this step. This is the most difficult one. So you need to check, you need to know that the overall rate of the reaction is going to depend upon this step only. And this step involves the formation of carbocation. So rate is directly proportional to the stability of the carbocation. Okay. And because you have taken solvent as the nucleophile, you can also note one more thing. Solvent is used for dissolving, and the solvent is actually coming in and joining itself. So the solvent is nucleophile. So this is known as solvolysis. Okay. The rate, if you write the expression for the rate, it is K times the concentration of the alkyl halide to the power 1. It depends only upon the rate concentration of this, because the slowest step had only this molecule, no nucleophile was coming in. So rate does not depend upon the concentration of the nucleophile. It is independent of the concentration of the nucleophile. You do not have any nucleophile, either the strength of the nucleophile or the concentration of the nucleophile, both are absent in this. The rate is not going to get affected because nucleophile comes in the second step, which is already fast. First, you need to check whether the Br is going to come out or not. Okay, whether the carbocation being formed is stable or not. If it is stable, then only the Sn1 reaction can happen. So substrate which can form a stable carbocation, example benzylic. Benzylic means if you have a benzene next to carbon. Okay. Tertiary alkyl halide. Tertiary alkyl halide is this one, the carbon connected to 3 carbon. That also can come out easily because the carbocation will be stable. Okay. And with weak nucleophiles, which are polar protect solvent like water, alcohol, which can do the hydrogen bonding and let the Cl or Br come out slowly. Okay, and these reactions are known as solvolysis. Like in this case, the solvent molecule is acting as a nucleophile, as you can see here. So let's do some questions. So the first question. So only one correct option is there. Which of the following is most rapidly hydrolyzed by Sn1 mechanism? You have Cl over here, you have Cl over here, you have Cl over here, and you have Cl on this option also. So all are Cl. Carbon chlorine bond is there, you need to break it and form a cation. Chlorine is same, it is not like the chlorine, bromine, or iodine. The iodine, if we would have iodine, that would have came out more easily. But now we have just chlorine. Its tendency to come out is same. But now whole things come to carbocation, whether the carbocation can form easily or not. So what are the factors which depend carbocation? Carbocation depend upon the number of alkyl groups or the number of benzene rings which are being attached. The benzene rings can stabilize the carbocation. As you can see, the carbocation has vacant p orbital, and the benzene rings, as you can see, have a lot of loose electron density in the form of pi electron cloud. So this empty carbocation, p orbital of the empty carbocation actually overlaps with this adjacent p orbitals of the benzene ring, which are filled and which contain pi electrons. So the energy of the carbocation, the electron density also comes and gets into this cation empty p orbital. So it becomes stabilized. And if you have three benzene rings, the extent of stabilization is just going to be thrice of the benzene ring when you have just one benzene ring. So this is benzylic cation. So, but there are three benzene. So each one of them is going to stabilize the carbocation very quickly. So now you can see this is the most stable. It can come out most easily. And this is the one which is going to undergo Sn1 reaction most quickly. Next question. This is very common question, where you can expect the silver white PPT of AgCl. Means you are removing the Cl, then only this is going to come and form with Ag. Where you are expecting the AgCl to come out most quickly. Okay, so same thing. Here the Cl is going to come out. Yes, because you have a carbocation. And the carbocation, here it is stable, but it is stabilized by only just one pi bond, electron density of the one pi bond. Here the Cl can't come out because the Cl itself is actually under resonance with this. So there is a partial double bond character. This Cl can come out easily because this is benzylic. And the first one also can come out easily. But this one can't come out because it is already forming a partial double bond. Here you do not have a carbon and then Cl. The Cl is directly linked to the benzene. So the lone pair of the Cl and the benzene are overlapping. So Cl is more tightly bound and it is not going to come out. So first one and the third one are going to come out easily. And they are going to quickly show the white precipitate of AgCl being formed. Got it? So now you need to arrange in the third question, you need to arrange the compound in decreasing rate of Sn1. So this is cation which is being formed adjacent to benzene, cation which is being formed adjacent to benzene. This is same in all the four substrate. You have Br same on all the four substrate. Now which thing is going to impact the rate of the reaction? You have a cation, the cation will undergo resonance. Okay, and how well this benzene can stabilize this cation, that's the point over here. On this substrate, on this benzene ring, you do not have any other electron donating group. Though the cation is stable by circulating itself on the benzene ring, but it will become more stable if there are more groups attached on the benzene ring and those groups are also electron donating, because carbocation loves electron. Carbocation is an electron deficient species. So this methyl, ethyl and isopropyl, they are electron donating species. But which group is most electron donating? it is methyl. Normally students say that it should be this one because it is more branched, and the alkyl group actually are electron donating. They are electron pushing groups. They exert plus I effect. That is true. But there is one more effect which is caused by the hydrogens of the alkyl group, and that effect is hyperconjugation. So this hyperconjugation effect, in which the methyl group or the alkyl group donates its electron density from the CH bond, and to measure the extent of stabilization you need to count the how many CH bond are there. So this group is going to stabilize the carbocation. Okay, so I hope this is true, clear. So this is going to be the most reactive substrate for Sn1, followed by, because it has most number of alpha hydrogens, followed by this one which is having 2 alpha hydrogens, and this one. Normally students give the reverse answer. They say 4, 3 and 2. No, but 2 is the most reactive. 3, 4 and 1 doesn't have any group, though there is a benzene. So out of all these, this is undergoing Sn1 by the lowest rate. So I hope this is clear to all of you. Let me move ahead. Solvent effect I already discussed. Okay, there is a hidden role of the solvent, right? So solvent actually helps. The solvent water is very important for Sn1 to happen. I explained you just now, and it can pull the leaving group apart. These are polar aprotic solvents. The delta plus is not accessible, you can see over here, so it is not going to help us. This is the solvent ideal for Sn2, polar aprotic solvent. But polar protic solvent, you have H plus directly connected, so H plus can pull the Br minus out, and that's how it is going to help Sn1 to takes place. But in polar aprotic solvent which are used in Sn2, the plus is there not on H plus, on some other atom, like here it is on sulfur. In this case it is on carbon. This delta plus is of no use. So this actually can stabilize only cation but not anion. First you need to pull out the Br minus or the Cl minus by solvents. For that you need solvent which has H plus. So protic is for Sn1, aprotic is for Sn2. Okay. Now what is the characteristic of Sn1 reaction? Let's see. So in Sn1 reaction, we have seen, in Sn2 reaction, we have seen, because everything was happening simultaneously, the attack of the nucleophile, the departure of the leaving group was happening simultaneously. So there actually, if you had more number of alkyl groups, they were causing problem. They were not letting the nucleophile to come and attack. Got it? So the rate was slowing down. But in Sn1, reverse thing happened. Sn1, there was no, that was not a single step reaction where the nucleophile was directly coming in and pushing out the leaving group. In Sn1, first you remove the leaving group, and the hidden role is played by the solvent. Once the leaving group comes out, and you are left with a carbocation. The carbocation should be stable. Okay. If it is stable, the leaving group can come out easily. If it is not stable, the Sn1 can't happen, then you should prefer Sn2. Okay, so you have a carbocation, and that carbocation is flat. carbocation is flat, means it is a trigonal planar geometry. So now the nucleophile can come and attach itself from both the sides. You form two products in which you observe that the nucleophile is attached from the same side as well as from the opposite side. Got it? So you get a racemic mixture. Racemic mixture is equimolar mixture of two opposite enantiomers. In Sn2, racemic mixture was not forming. You were getting only the inverted product. In Sn1, because there was a carbocation which was free to be attacked from both the side. In Sn1, you are getting a racemic mixture. Now this is the comparison of Sn1 and Sn2. Sn2 single step, Sn1 multiple step, two main step which involves carbocation. This is bimolecular because two molecules were attacking. This is unimolecular. First molecule was actually breaking into carbocation and leaving group. Rate is controlled by steric hindrance. If you have more large groups attached to the carbon, the rate is going to slow down. Rate is controlled by the stability of carbocation. If you have benzene rings or if you have doubly bonded groups which can stabilize the carbocation by resonance, the rate is going to go up. Okay, methyl, primary, secondary halides can undergo Sn2 but not tertiary. Tertiary alkyl halides are too bulky. Nucleophile can't come in and join itself. Okay, other tertiary Sn1, only tertiary alkyl halide undergo Sn1 solvolysis. Okay, tertiary alkyl halides, or if you have a benzene ring which can stabilize the carbocation, okay, there also you can have Sn1. Product have inverted configuration, that is known as Walden inversion. Here the product is retained as well as inverted configuration. You get the equimolar mixture of two components together. Okay, so this is actually racemization happening. Leaving group tendency affects the rate of Sn2. It also affects the rate of Sn1. This is common thing happening in both, because if the group doesn't want to come out, you can't do either Sn1 or Sn2. Better the nucleophile, faster is the rate of reaction, because nucleophile in Sn2 was attacking directly and initiating the reaction. But in Sn1, the strength of the nucleophile and the concentration of the nucleophile do not affect the rate of Sn1, because it was appearing in the fast step. The main step was departure of leaving group where no nucleophile was there, only carbocation was formed. So carbocation stability was the key factor for determining the rate of Sn1. Got it? So I hope this is clear. Okay. Now these are the mechanisms. Now let's see the applications. So preparation of RX, preparation of alkyl halide from alcohol, and the one method is actually you use HX. You use HBr, HCl, and that actually removes the water, and you have X. You have, if you take NaBr, the reaction is not going to happen. You require H plus. Actually, wherever in organic, whole of the organic chemistry, wherever you want to remove the OH, wherever you want to remove the OH group, you need acidic medium. The acidic medium protonates the OH, and that actually removes this, okay, forming a cation. Look, it makes the OH a good leaving group, and it facilitates the reaction to take place. And this reagent has a specific name, Lucas reagent. This is also used to distinguish between primary, secondary, and tertiary alcohol. How? Because this RH doesn't mix with the alcohol and it imparts cloudiness or turbidity. It imparts cloudiness, turbidity to the reaction mixture. How quickly the reaction has progressed or completed, that depends upon how quickly the turbidity or the cloudiness has appeared, how quickly it has appeared. And this is Sn1 mechanism. And Sn1 is directly proportional to the stability of carbocation. Methanol is going to be the slowest. Ethanol is going to be the more than this one. Then you have isopropyl alcohol, which is a secondary carbocation. And the most reactive is tertiary. So tertiary alcohol reacts instantly and you get turbidity in just 1 to 2 minutes. Means the reaction gets over in just 1 to 2 minutes. In secondary, the reaction with Lucas reagent, you require 5 to 10 minutes. In primary, because the carbocation is not stable, it is going to form with difficulty. Primary doesn't give you Sn1. So either they will say no turbidity, or they will say the turbidity is going to appear after 30 minutes or half an hour, or the turbidity is going to appear only upon heating. It is indirect way of saying that you have taken primary alcohol. Turbidity or haziness or cloudiness is because of the formation of alkyl light. Time for the appearance of turbidity tells us how quickly the reaction has progressed. This is Sn1 mechanism. So how quickly the reaction has progressed? It is told by turbidity, the time for the appearance of turbidity. So it is used to test primary, secondary, and tertiary alcohol. It is used to test primary, secondary, and tertiary alcohol, and it is also used for the conversion. You can see if you react with HI, the water is going to come out and you are going to have iodopropane. If you react with HBr, you are going to get bromocyclohexane. Okay, this is how the reaction will progress. Got it? Some other examples. But this is not the intention here, is just the conversion to bromide or iodide by reacting with HI, or chloride by reacting with HCl. But here the intention was conversion as well as to identify what type of alcohol we are dealing with. So there you require zinc and ZnCl2 and HCl. So that the time for the completion of reaction, how easily it has completed, is can be predicted by can be used to predict the type of alcohol. So what is the answer to this problem? Very famous, and you know this is going to come out very easily. And this OH, all these reactions are applicable only to aliphatic alcohols. Aliphatic, not on aromatic alcohols. They are not going to come out at any cost, because they are in resonance with the benzene and they have double bond character. So here you are going to get OH and CH2Cl. So if you have not taken HCl, you can use NaCl and H2SO4 to get HCl. But this H2SO4 should not be used with Ki to prepare HI. What's wrong with H2SO4? Here you are using it to get HCl and NaHSO4. But why you are not using with Ki? The reason being, HI form is a very good reducing agent, and H2SO4 exhibit oxidizing character. It takes away the electron, so you get I2. So whole of your HI will get spoiled, and SO2, it will get spoiled up. So now you do not have HI. So now that it cannot react with alcohol. So you should not use H2SO4. If you want to get HI from Ki, the appropriate acid is the one which will not oxidize. It is phosphoric acid. Non-oxidizing acid you should use, so that the HI which is being formed do not get oxidized. So this is the Lucas I already told you. It is used to differentiate different type of alcohols. This is basically Sn1 reaction. Okay. If the carbocation bond is stable, then it can come out easily, and the immediate reaction, immediate turbidity you are going to observe. Okay. There is other method which is SOCl2. This is considered Darshan's process and considered to be the best method for conversion of alcohols to alkyl halides, because all the byproducts which are there, they are gases, so don't have to separate them. You get pure RCl. Okay. So this is the other method is by treating with phosphorus halides. Phosphorus halides, either you can use PCl3, PCl5, or you can use P plus X2 also. That also will react and give you PCl3, PBr3, or PI3, but not Cl2. It is difficult because chlorine is a gas. So you don't use chlorine because it is hazardous and it will not, it is difficult to handle. But if it is given in the question, red phosphorus and chlorine, you assume it to be PCl3 and convert the alcohol to chloride. So these are some of the important reactions. So let me complete. This is almost complete. Some elimination we need to see. On the next turn we will complete it. Just in